This presentation illustrates how the landscape that surrounds us came into being. For most of our geologic history, Sedona and the Verde Valley were on a coastal plain. Our story today involves nearly 440 million years of sedimentary materials being deposited on that coastal plain or just below it. These materials form the sandstones, limestones, and other sedimentary layers that surround us today. These sedimentary layers were then raised by tectonic forces, exposing them to the forces of nature. The sandstone and limestone layers were then sculpted over the past 80 million years to their present form by uplifting, faulting, volcanic activity, and most importantly, erosion.
Hi, my name is Mike Ward. I'm not a professional geologist, but I've always been fascinated with geology. I came from the Midwest, where it's all glacier till and the occasional moraine. I mean, who cares? But out here, geology's in your face. Recorded in the rocks around the Verde Valley in Sedona is over 1,800 million years of the Earth's rock history.
The state of Arizona is divided by 3 geologic zones. To the north is the Colorado Plateau that covers most of the 4 corner states and is where the Earth's crust was uplifted mostly intact. The transition zone, where Sedona and the Verde Valley are, many small blocks of the Earth's crust were uplifted mostly intact, but separated by vertical displacements. And to the south and west, the Basin and Range, extending up through Nevada, where the Earth's crust was extended, broken up, and in geologic terms, quickly eroded away. Think of books on a bookshelf, where the bookends are removed, and the books fall over and slide apart. This illustrates the transition zone, where small blocks of the Earth's crust were pulled apart and squeezed together through time, causing the blocks to be faulted, raised and lowered relative to the blocks on either side. Before we can continue, we need to have an understanding of geologic time and geologic forces. They are so immense that it's difficult to get one's mind around it. Geologists generally show geologic time as shown in this graphic. Usually, the Phanerozoic period is broken out from the full-time column as a second scale timeline. Then from the second column, the Cenozoic era that corresponds to the age of mammals is again broken out into a third column. In the second timeline scale, the 11 periods are divisions of biological life forms between 10 mass extinction events. Extinction events are defined as points in the geologic record where 50% or more of life forms suddenly disappear. Of the 10 major extinction events, there were 5 great mass extinction events that divide Earth's history into 5 distinct ages. These are typical index fossils that geologists look for to date sedimentary rocks. The geologic time during which these creatures lived is generally agreed upon. The sudden absence of these index fossils from the fossil record are evidence of a mass extinction event. Therefore, the presence or absence of these index fossils in a specific layer allow geologists to be able to date that sedimentary rock layer. Although life had its beginnings several billion years ago as single-celled creatures, around 600 million years ago, the Earth completely froze over and is referred to as snowball Earth. Glaciers covered the land masses and the seas turned to slush. Although there is no fossil record, it can be assumed that whatever life forms there were, they were either eliminated or perhaps only the fittest life forms survived. A thawing snowball Earth ushered in the Cambrian life form explosion, and the age of invertebrates, which coincidentally is when the oldest sedimentary rock formations in this area were layered down. About 439 million years ago, the age of invertebrates came to an end with a mass extinction, and gave rise to the Age of Fishes. Then again, about 364 million years ago, another mass extinction that closed the Age of Fishes and gave rise to the Age of Amphibians. The Age of Amphibians came to a close 251 million years ago with the Permian extinction, sometimes called the Great Dying, when over 95% of all life forms that then existed disappeared from the rock record. The Permian extinction happened just after the Kaibab Limestone Formation was layered down on the rim above Oak Creek Canyon. The Permian extinction ushered in the Age of Reptiles, which was then interrupted at the end of the Triassic period by an extinction event most likely caused by massive floods of lava erupting from out of the earth, forming the Atlantic Ridge, which triggered the breakup of the last supercontinent, Pangaea. The last great extinction event was the famous KT extinction 65 million years ago, which was caused by a giant asteroid smashing into the Earth and ending the reign of the dinosaurs, giving rise to the Age of Mammals. The problem with geologic time is that it is so vast, it defies our ability to comprehend it. If we talk about 100 years ago, or even 5,000 years ago, we can understand that length of time because we have human recorded history as a background to understand that length of time. But what's a million years? 10 million years? 100 million years? Let alone a billion years of Earth history. When I published my book on Sedona and the Verde Valley's geologic history, So Why Are the Rocks Red?, I attempted to make geologic time comprehensible. I divided the 4.5 billion years of Earth's geologic history into a geologic calendar comprised of 12 months. Each month of that geologic calendar equaled 365 million years. A day equaled 12 million years. An hour, 500,000 years. And a minute, 8,000 years. The middle column represents the last 50 days in that geologic calendar, and the third column represents the final 5 days of that geologic calendar. Going by this geologic calendar, the basement rocks beneath us were formed August 3rd. The Tapete Sandstone, the oldest known sedimentary rock in the Southwest, was formed in later November, sometime just before Thanksgiving. The Red Rocks of Sedona, the Schnebly Hill Formation, were formed around December 8th. The Laramide orogeny, when the Southwest was uplifted over 2.5 miles, happened around Christmas Eve and Christmas Day. Modern man, who's been around for about 250,000 years, has been in existence since 11:29 p.m. of New Year's Eve. And man has been in the Sedona area for about 10,000 years. That's only the last minute, 11:59 of New Year's Eve of our geologic calendar. Let's talk about the geologic forces of nature that shaped our landscape. The first is deposition. Sandstone is formed by the compression of sand and other materials laid down by the wind. Limestone is formed by the compression of the skeletal remains of marine life. Preserving these layers is a function of the Earth's crust being down-dropped below sea level, protecting the sedimentary layers from erosion by wind and water. Then there's erosion. Erosion is a function of the Earth's crust being uplifted above sea level, exposing the sedimentary layers to the effects of wind and water, allowing them to be eroded away. It has been said that Mother Earth is the consummate rock recycling machine. In an attempt to put the forces of erosion into perspective, Consider the Grand Canyon. The Grand Canyon is 277 miles long. On average, it's 10 miles wide and a mile deep. Using simple geometry, it averages 5 square miles in cross-section. There is 2,770 square miles of area below the rim of the Grand Canyon. By multiplying the cross-section by the length, gives us 1,385 cubic miles of rock. That equals about 2.5 billion tons. Now, the Grand Canyon has been forming over 6 million years. So dividing the number of tons by 6 million, we get an average of 462.2 tons of sedimentary rock removed every year. So where does all that eroded rock go? Let's look at the Mississippi River Basin. The Mississippi drains 1.2 million square miles. The river is essentially a conveyor belt that moves 150 million tons. That's equivalent to 85.25 cubic miles of sediment down into the Gulf every year. Now, for comparison with the area of the Grand Canyon, for every 2,770 square miles in the drainage area, the Mississippi River and all its tributaries carry away to the Gulf of Mexico 346,552 tons of sediment every year. Another force to be reckoned with in Arizona is volcanism. This is the surface geology map of the rock formations in Arizona. Let's just consider the 2,770 square miles equivalent to the area of the Grand Canyon surrounding Sedona. The areas that are colored dark brown is the surface area covered by volcanic basalt today. Now let's just assume that the entire 2,770 square miles was covered by 600 feet of basalt between 6 and 13 million years ago. That works out to 314 cubic miles of basalt having erupted from volcanic vents around Sedona. So what does 600 feet of basalt look like? This is Rorick Canyon off Blue Gray Road, just southeast of I-17. My topo software that I use for hiking indicates that the depth of Rorick Canyon is a little over 600 feet, carved through a formation of solid basalt. Another important geologic force is the faulting of the Earth's crust. There are hundreds of faults throughout Sedona and the Verde Valley area. The Verde Fault, for example, runs through Jerome, and the displacement is over 6,000 feet. How do they know that? Core sampling discovered the Hickey Formation 2,000 feet below the city of Cottonwood. The Hickey Formation's on the top of Mingus Mountain, and Mingus Mountain is 4,000 feet above Cottonwood. The total displacement is 6,000 feet. The Oak Creek Fault is approximately 1,000 feet of displacement, when the east side of Oak Creek faulted downward along the Oak Creek Fault. The Cathedral Rock Fault, which runs along the Baldwin Trail, is approximately 100 feet of displacement. If you stand on the Fort Apache limestone on the saddle of Cathedral Rock and look at Napoleon's tomb, there's a sandstone tower on the top of the tomb that is capped with the Fort Apache limestone. The Fort Apache limestone on Napoleon's tomb is 100 feet lower than the Fort Apache limestone in the saddle of Cathedral Rock. In the 1970s, geologists came to understand that the Earth's crust is comprised of 15 independent tectonic plates that move around the Earth's surface over geologic time. The term that geologists use today is plate tectonic. When planet Earth was little more than a frozen ice ball 650 million years ago. Sedona was located near the South Pole on the remains of a supercontinent named Rodinia. The following sequence of slides demonstrate how Rodinia broke apart as the 15 independent plates drifted away from one another. Over geologic time, the tectonic plates recombined to form the supercontinent named Gondwana. Gondwana then broke apart, and the drifting tectonic plates eventually recombined to form the supercontinent that we call Pangaea. The place we know of as Sedona was north of the equator when the red rocks of Sedona were deposited in the middle of the Pangaean supercontinent. Toward the end of the Triassic period, Pangaea began to break apart and eventually formed the world map as we see it today. The North American continent is drifting ever westward and will eventually collide with Australia and Asia to build yet another supercontinent. Pictured here is a cross-section of Sedona and the Verde Valley as we see it today. As illustrated on the terrain model located in the Red Rock Ranger District Visitor Center, the cross-section represented by the red line stretches about 33 miles from the east side of Oak Creek Canyon to the Mingus Mountain Recreation Area and roughly follows State Route 89A. For the purpose of the animations, the actual profile shown here is exaggerated by a factor of 6. In the animations illustrating the tectonic movement of Sedona and the Verde Valley, sea level will remain constant, representing the geologic average sea level. The black profile line represents Sedona and the Verde Valley's current topography and elevation. To demonstrate Sedona and the Verde Valley's location above or below sea level through time, the elevation profile drops down and uplifts with the geologic rock formations. Sedona and the Verde Valley's rock stack rests on a Precambrian foundation termed the basement rocks that were formed 1,800 million years ago. The formation is called the Yavapai Group, and it contains a granite intrusion known as the cherry granite. The cherry granite can be viewed where it has been uplifted through time near Prescott, in an area now known as the Granite Dells on State Route 89A. The Tapeats Sandstone is the oldest sedimentary rock formation in the Southwest and was formed 550 million years ago. But the Yavapai Group below it was formed 1,800 million years ago. So where are the missing 1,300 million years of rock record? This gap in the geologic rock record is called the Great Unconformity, a period during which unknown numbers of formations were repeatedly deposited and then eroded away, leaving no trace. For most of Sedona's geologic history, the area was located on a coastal plain, either slightly below or slightly above sea level. Beginning 550 million years ago, sand dunes deposited along the seashore became the Tapeats Sandstone. This layer can be seen in the Verde Canyon near Sycamore Canyon. Over the following 420 million years, the North American plate, upon which the American Southwest lies, continually dropped below sea level, as shown by the white arrow. Then approximately 500 million years ago, as the land continued to slowly drop downward, the Martin Limestone Formation was deposited below a shallow sea that covered the Verde Valley and Sedona. Then beginning around 370 million years ago, the Redwall Limestone Formation was deposited on top of the Martin Limestone Formation. The Tapeats Sandstone, the Martin Limestone, the Redwall Limestone, and the Supai Sandstone Group can be seen here in Verde Canyon, near Sycamore Canyon, northwest of Clarkdale. The Supai sandstone group was laid on top of the red wall limestone, deposited between 330 and 290 million years ago on the coastal plains that surrounded Sedona and the Verde Valley. Pictured here is the Supai group sandstone in Oak Creek Canyon below Midgley Bridge on State Route 89A. Around 290 million years ago, mud and silt flushed down rivers onto the coastal plains that surrounded Sedona and the Verde Valley. These deposits formed the Hermit Formation upon which Sedona is now built. This is a photo of the Hermit Formation on State Route 89A on Cook's Hill, just west of the post office in Sedona. As the land continued to drop, the famous red sandstone cliffs that surround Sedona today was deposited on top of the Hermit Formation on a coastal plain that surrounded Sedona between 280 and 276 million years ago. As pictured on Twin Buttes, the Schnebly Hill Formation is comprised of three members. The lower member is the Bell Rock member that comprises Bell Rock. The Bell Rock member erodes as a slope because of the clay and silt that is intermingled with the sand. The 10-foot thick Fort Apache limestone member pinches out, disappearing north of Sedona, and caps Bell Rock. The topmost layer is the Sycamore Pass member that forms the vertical cliffs in the Schnebly Hill Formation. Pictured here is the Fort Apache limestone at Merry-Go-Round Rock. Following the deposition of the Schnebly Hill Formation, desert sands blown in on the wind created sand dunes that were hundreds of feet thick. Think of the Sahara Desert. They were deposited on an arid coastal plain that surrounded Sedona between 276 to 275 million years ago. These sand dunes formed the beige-colored Coconino Sandstone Formation seen far above Sedona. The line separating the Schnebly Hill Formation from the Coconino Sandstone is indistinct and is usually placed above wherever the last reddish sandstone is observed. A major characteristic of the Coconino Sandstone is the cross-bedding, revealing the leeward side of slopes of the sand dunes that made the Coconino Sandstone. Between 274 and 270 million years ago, the Torowheap Formation, which is a composite of sandstone and limestone, and the Kaibab Limestone Formation were deposited in the shallow seas that covered Sedona and the Verde Valley. After the Kaibab Limestone was deposited, the Great Permian extinction wiped out nearly 95% of all marine and land life forms and ushered out the age of amphibians, giving rise to the age of reptiles. The Schnebly Hill, Coconino, Torowheap, and Kaibab formations are visible at West Fork in Oak Creek Canyon. Over the next 100 million years, successive layers of sedimentary rock formations were layered above Sedona and the Verde Valley. As the Kayenta Formation was deposited in the early Jurassic period, dinosaurs walked throughout Arizona. As you drive a short distance from State Route 89A on 160 toward Tuba City, it is possible to stop at marked locations along the road to view the tracks left behind by the dinosaurs that roamed what is now Arizona. Over the 500 million years of downward movement of the North American tectonic plate, 12,000 feet of sedimentary rock had been deposited. By 80 million years ago, nearly 7,000 feet of sedimentary rock deposits are believed to have been layered over the formations around current Sedona and the Verde Valley. Because the Colorado Plateau tilts downward toward the northeast, these formations are visible as you travel toward Kayenta on State Route 160. These formations are labeled with question marks next to the names, as they are known on the Colorado Plateau. Since these layers are long eroded away and have left no trace that they were ever here, they are shown grayed over. At this point in time, present-day Sedona was buried under nearly 1.5 miles of solid rock. Beginning in the late Cretaceous period, while Pangaea was breaking up, and while dinosaurs still dominated the planet, a small South Pacific plate named the Phaleron Plate began subducting beneath the North American continent. As the Phaleron Plate pushed against and slipped under the North American continent, the tremendous tectonic forces compressed and lifted the North American continent, warping the continental crust. This 40 million year uplifting event is known as the Laramide orogeny. The immense pressures caused by the collision between the two tectonic plates fractured North American continent. These fractures are termed fault lines, separating individual slabs of the Earth's crust. As the North American continent was being lifted, the sedimentary rock formations were being exposed to the erosional forces of wind and flowing water, and were gradually eroded away. After 40 million years of upward movement, the Laramide orogeny ground to a halt as the Phaleron Plate completely subducted under the North American Plate. Toward the end of the Laramide orogeny, the Verde Fault that passes through Jerome became active. The basement rocks beneath Mingus Mountain and Jerome were gradually squeezed upwards to expose the Cleopatra Tuff above Jerome and Mingus Mountain rhyolite along State Route 89A above Jerome. Evidence of this uplift is the Tapeats Sandstone, pictured here above Jerome. Only a few miles away, the Tapeats Sandstone is down at the Verde River. Along State Route 89A, above Jerome, ancient beds of rhyolite in the Yavapai Formation bedrock dominate the landscape. West of Mingus Mountain, along State Route 169, the landscape is dotted by exposed pieces of cherry granite embedded in the Yavapai Formation bedrock. The area is covered completely by decomposed granite from the eroding cherry granite. Road cuts along State Route 169 expose the bronze-colored decomposed granite. The pure granular decomposed granite can easily be scooped up by the hand. After the Phaleron Plate completely subducted under the North American continent, the Basin and Range Extension event was a period of great volcanic activity. The linear distance between the Black Hills and the Mexican border nearly doubled, pulling the Earth's crust apart. Think of books on a bookshelf. When the bookends are removed, the books fall over and slide apart. This is what happened to southern Arizona and most of Nevada. Approximately 13 million years ago in the Sedona area, lava from Mingus Mountain and House Mountain, located just south of Sedona, covered the area with hundreds of cubic miles of basalt. These basalt layers are termed the Hickey Formation and the House Mountain basalts. House Mountain, located to the south of the village of Oak Creek, is a large 13 million year old shield volcano, as viewed from State Route 89A near the wastewater treatment plant. Road cuts along State Route 89A between Sedona and Cottonwood expose the basalt flows from House Mountain. As the many area volcanic vents continue to pour basalt lava across the land, beginning approximately 10 million years ago, near the end of the Basin and Range Extension event, the crust of the Verde Valley was pulled apart, forming new fault lines. This was the beginning of the Verde Valley. Pictured here is the throat of a large volcanic vent, as seen from the saddle of Cathedral Rock. This vent is one of perhaps hundreds that dot the area. Most are covered by soil, eroded away from higher elevations. To appreciate how large this vent is, look at the two people climbing around on the basalt. As fractured segments, of the Earth's crust were downdropped along the newly formed fault lines, the Verde Valley Graben began to form. This is one of the many fault lines between Sedona and Cottonwood. This is the Dry Creek Fault in a road cut along 89A near Dry Creek. As the lowest point in the area, water began collecting in the Verde Valley Graben, forming what was to be known as Lake Verde. Over millions of years, the escarpments along the fault lines were eroded away, washing into Lake Verde and mixing with the Verde Formation as the Verde Valley Graben continued dropping downward. The Verde Valley Graben continued to drop downward. As Lake Verde expanded and deepened, the skeletal remains of marine life were deposited at the bottom of the lake. These deposits would form the freshwater limestone of the Verde Formation. Over a period of 8 million years, the Verde Valley Graben downdropped approximately 6,000 feet. Lake Verde deposited the freshwater limestone that comprises the Verde Formation to a depth of approximately 2,500 feet. To the east, the Hickey Formation and the House Mountain basalts eroded away in the area that would become Oak Creek Canyon. Wilson Bench slips down along Oak Creek Fault as the east side of the canyon drops nearly 1,000 feet. Viewed from State Route 179, the basalt of Wilson Bench that slipped down along the Verde Fault about 780 feet shows how much Wilson Mountain basalt covered the area. The basalt on the east side of Oak Creek Canyon came from the Wilson Mountain event. Approximately 2 million years ago, Lake Verde drained away and was replaced by a flowing river now known as the Verde River. And for the past 2 million years, the Verde River has meandered through the Verde Valley, carving out the soft Verde Formation, creating the valley that we see today. Flowing waters from the Colorado Plateau, supplemented by groundwater, began carving out today's Oak Creek Canyon, while wind and flowing waters sculpted the magnificent red rock landscape that we call Sedona. This is Oak Creek Canyon as viewed looking northward from Wilson Mountain. The basalt cliffs of the east side of the canyon is obviously much lower than the west side. As viewed from Clarkdale, the freshwater Verde Formation along the Verde River towers over the town. The Verde Formation extends downward more than 2,000 feet. The Verde River, as seen from the Verde Canyon Railroad, cuts 150 feet down through a basalt flow that came out of Sycamore Canyon. The final chapter in the geographic morphology story is the formation of the 7 unique sinkholes that populate the area. The 7 sinkholes occur in the surface bedrock of the Supai Sandstone, Hermit Formation, and Schnebly Hill Formation, but the cause is from the collapse of subsurface water-filled caves in the Redwall limestone that underlies those formations. The most famous, although not the largest, of these sinkholes is Devil's Kitchen, number 1, located on the Soldier Pass Trail. Devil's Kitchen will be examined more carefully in the animation that will follow. The Mitten Ridge sinkhole is listed as number 2. Access to the site is made from the Cowpies Trail. Well hidden, the Mitten Ridge sinkhole is located at the base of a steep and massive cliff located in the northeast and prominent saddle on Mitten Ridge. Mitten Ridge is an unusual sinkhole because of the high elevation at which it is exposed above the presumed deep-seated Redwall limestone cave collapse. The interior walls of the 18 by 24 Mitten Ridge cavern are completely fractured, while the flat roof is composed of massive, unbroken Schnebly Hill sandstone. The small sinkhole collapse is estimated to be 1,100 feet above the top of the Redwall limestone formation. Devil's Dining Room, number 3, is located on the Broken Arrow Trail, about 3/4 of a mile from the trailhead. Devil's Dining Room is situated near the top of the Hermit Formation, where overlying Schnebly Hill sandstone has been eroded away. Devil's Dining Room is 27 feet in diameter. The top of the rubble pile that extends down into the Red Wall Limestone Formation can be seen about 70 feet below the edge of the sinkhole. It is easy to see the volcanic dike surface at the back of the sinkhole, filling the joint that forms the back wall. Devil's Dining Room is a significant area of bat habitat in the Sedona area. Located a short distance from the Turkey Creek Trail is the Turkey Creek Sinkhole, number 4. A weathered sandstone outcrop is exposed at the top of a shallow, oval-shaped crater, about 30 by 55 feet across the bottom. The Turkey Creek Sinkhole may be one of the older sinkholes in the area, and material found in the bottom of the sinkhole suggests that it was used as a dump by the early settlers. The Nolan Draw Sinkhole, number 5, is located to the west of Forest Road 525 near the intersection with Boynton Pass Road. Nolan Draw is about 46 feet by 56 feet, and the irregularly shaped hole has an area of about 1,830 square feet. The dirt-covered eastern floor of the sinkhole lies at a maximum depth of 68 feet below the bedrock lip. While most Sedona sinkholes enlarge downward, the Nolan sinkhole displays the most dramatic increase in the undercut enlargement. This illustrates another example of the bell-shaped downward enlargement of the sinkholes overlying the Red Wall limestone. Red Canyon Sinkhole is by far the largest sinkhole in the Sedona area. It lies on the eastern side of the Palaki Heritage Archaeological Site. The western and northern walls of the Red Canyon Sinkhole are composed of Schnebly Hill sandstone walls with a sheer drop of 100 feet to the deepest part of the sinkhole. Sinkhole 4543, designated number 7, is in its formative stage, located at the base of Bear Mountain. Shown here with a person standing in the sinkhole to demonstrate scale, it has a circumference of 13 feet and a depth of around 3 feet. It is the smallest of the Sedona area sinkholes. The name 4543 is taken from the elevation at the site and was assigned by Paul Lindbergh, a well-known geologist. Lindbergh believes that 4543 is a sinkhole that is probably in the formative stage of breaking through to a modern ground surface. He goes on to note that a substantial amount of air rushes in and out of 2 small rock openings at the site, indicating a very large cavity somewhere below ground level. As the Verde Valley graben dropped, both surface water and groundwater flowed towards and under the Verde Valley from the Colorado Plateau to the north and east of Sedona. As snowmelt from as far away as the Rocky Mountains and groundwater percolated down into the rock formations below, the water worked its way into the Verde Valley, always seeking the lowest level. Collecting in the Red Wall limestone, the groundwater in the aquifers are slightly acidic, enough so that it dissolves calcium in the Red Wall limestone as it flows through the rock. Cavernous tunnels are formed through which underground rivers flow. Once cavern rooms grew large, the ceilings of some of these caverns would sometimes collapse, creating sinkholes, as layers above pancaked downward. As rainwater and snowmelt seep into the ground, it collects carbon dioxide, making the water slightly acidic. It collects in aquifers when the water is blocked by impervious rock formations below it. Around Sedona, the aquifer flows through the Red Wall limestone. The slightly acidic groundwater passing through the Red Wall limestone dissolves the limestone, creating a network of cavities and voids. As the limestone dissolves, pores and cracks are enlarged and carry even more acidic water. As the caverns grow in size, the unsupported ceilings of the caverns can collapse, expanding the caverns into the rock formations above the aquifer. Over time, successive rock formations pancake downward because of cracks and breaks in the rock formations that cause the cavern ceilings to give away. Around 1880, early settlers in the Sedona area reported the sound of a tremendous explosion. Investigating the source of the calamity, they found a sinkhole had been formed. In 1989, a large section of rock broke away and fell into the sinkhole. Located at the surface level of southwest corner of Devil's Kitchen is a fracture that has been documented by Paul Lindbergh. This fracture has been widening over the past several decades. What was in the 1970s a 2-inch opening is now 7 to 11 inches wide, located 4 to 15 feet back from the western edge of the sinkhole that suggests the sinkhole remains very active. Frost heaving and rock wedging will ultimately cause this piece and another similar block to the north to break loose and unload into the sinkhole in a future collapse.